Okay. You guys remember how to take the derivative of the exponential function with a particular constant base b to the power of x. What is that derivative formula? I'm checking chat for the derivative formula. I'm checking chat for the derivative formula. There you go. You make sure that all of you remember that the derivative of an exponential function is always that same exponential function multiplied by a constant. That constant is the natural log of the base. When the base is e, the natural log of e is 1, and so e to the x is the one where the derivative is actually just e to the x. Now, for the sake of notation, I'm saying that g of x is f inverse because it is very, very awkward to try and say the derivative of f inverse. So we're going to remember the formula we learned yesterday about derivatives of inverse functions. So do you remember a word that you would use for the derivative of inverse functions? A word. Yep, reciprocal. So the derivative of g of x is 1 over the derivative of its inverse, but not at x. What do I have to plug in to f prime? Correct, the y value. And the y value of your g of x function, your inverse function. So in this case, that means log base, if I can write, log base b of x is what we're going to be plugging in. That means I'm going to come over here and I'm going to look at this formula, and that is the f prime, and I'm going to plug this in. So g prime of x is equal to 1 over constant natural log b times b to the power of log base b of x. And take a moment to remind yourself, what is b to the log base b of x? It is simply just x. So you need to memorize this formula. And additionally, what does that mean is the derivative when the base is e? When the base is e, what does that make the derivative? 1 over x, just plain 1 over x. You're going to be using the 1 over x a lot. It's going to be a rarity that you have to remember this formula, but you need to remember it. I'm going to throw it on tests, make sure that you have that memorized. And it's not the natural log of x. It is the natural log of b as a constant. It's a constant multiple of x in the denominator. And I also want to mention over here that the domain of f inverse, because it's a logarithm, is, checking chat. Oh, right here, I said when the base is e. So that's coming over to this. What is g of x? How do we write it when the base is e? And we write it with natural log, with ln. And then that's just understood to be our base e logarithm. If my function is a logarithm, what is its domain? Correct. Positive numbers only. 0 to infinity. Take a moment to also think about exponential functions. When you graph an exponential function, it's completely above the x-axis, right? Exponential functions have a range of only positive real numbers, but logarithms have a domain of only positive real numbers. So that means that when you take this derivative and get 1 over x, you've got to be careful because 1 over x lets in a whole lot more than just positive numbers. And that's a cautionary tale. And I'm saying if g of x is natural log x or log base b of x, the domain of g prime is 0 to infinity. If I want more domain than that, I need to look at this h of x function. And if you see natural log of absolute value of something, it's not going to show up very often. This is actually a bigger issue to prep you for when we have to go backward. And by backward, I mean solve integrals. So take a good look. When I absolute value that x inside natural log x, that means if x is greater than 0, the function is just natural log x. But if you're dealing with a negative number, when you multiply it by -1, you make it a positive number going in the logarithm. And that does the same thing as that absolute value does. So now, what did we learn to be the derivative of natural log x? So if x is greater than 0, what is the derivative? 1 over x. In order to find the derivative of the natural log of negative x, we have to recognize a baby function. So when I use the chain rule and I say blah, that's referring to just whatever's in the position of the variable. So if your function is the natural log of blah, what is the derivative? It is 1 over blah. So then I'm going to take that baby function, negative x, give mommy her baby, and then I'm going to multiply by the derivative of that baby. What is the derivative of that baby? -1. So guess what? That means the derivative of h of x is officially 1 over x for all real numbers except 0, because it's kind of a problem when you divide by 0. Now, the main reason you need to be aware of this is, first of all, keep an eye on domain issues. Secondly, just to remind you, if you look at the graph y equals 1 over x, can you picture it in your head? Maybe, maybe not. Wee! Wee! Were you picturing that with the asymptotes for the axes? Now, when you're looking at 1 over x, its domain is all real numbers except for 0. If you are told that the derivative of a function is 1 over x, so let's say you are told that k prime of x is 1 over x, and then they ask you, what could k of x have been? If you don't put absolute values around x when you say natural log x, you have lost half of the domain. instantly. So this is going to be an issue later on. And I'm pointing it out now so I don't have to, at that time, go over this again. Because I don't want to go over that again. Confused why g prime of x has a different domain than h prime. Because g prime is coming from the natural log of x. So basically, the domain of g of x is only numbers that are positive, x greater than 0. Its derivative cannot add to the domain. So the derivative is forced to have its domain be only positive numbers. And if you look at those, yeah. So let me grab my Desmos, and I'm going to Desmos this. Oh, that was supposed to be an equal sign. There we go. So if you look at the entirety of 1 over x, you see that there's a problem. The logarithm is only existing when x is greater than 0, so its derivative should only be this right half. I can tell Desmos to graph only that right half. Okay, I really would like it if it wouldn't do that, because now I can't get... I don't know how to make this move. Does anyone know how to make this move? Because I don't. Oh, I pushed the X to hide tools. Ah! Oh, I didn't want it there. If you put these brackets on, you can then say a domain to stay in, and it'll only graph that domain. And if you spend time looking at these slopes, you will see that. In fact, I could... Let me do this. I'm going to go ahead and do this. I'm going to duplicate that. Oh, that went back to the... whatever. Okay. Stop. So I changed the f of x function to being just natural log x. And let's see. There is its derivative. Does that definitely look like what we just saw with 1 over x? Try and put it in the same position. Oh, I know. I go home, and then they go in the same positions. Doot, 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 doot. Yay, it's the same thing. Okay, so that is what you need to know. And then I'll make another video where I go over some examples of just taking derivatives with log functions before you head into your homework. Now, next thing is, in section 3.7, they go through a lot of applications. With an AP class and limited time, I'm only going to do the linear particle motion aspect, or part of that. Some of you might find it interesting if you read over section 3.7 to see a variety of applications in a variety of scientific fields. But we're going to focus on this. We've talked about particle motion a little bit already, and now we're going to add to that. Here we go. So first, recall that the actual motion when you're dealing with linear particle motion, hey, you came back. The actual motion is only back and forth on a line. It could be a horizontal line like I have drawn here, but it could be a vertical line. It could be some diagonally line. But there is a 0 point, there is an understood positive side and an understood negative side. In physics, you get to decide what's going to be a positive side and a negative side of 0. Here, we go with the Cartesian version of horizontally, right's positive, left is negative. Vertically, up is positive, down is negative. And other than that, you have to be told what would be a positive versus a negative direction. Now, you should remember the relationships of your three functions. And I want to remind you, we have to use the letter S for position function, not D. And the relationship is that to get to acceleration, you have to do second derivative of position, which is the first derivative of velocity. And you can get to velocity by taking the first derivative of position. Now, what determines the direction of motion along a line? So, if I am moving to the right, between the position function, the velocity function, and the acceleration function, one of those three really nicely tells you whether you are moving to the right or to the left, which in other situations interprets to moving up, moving down, or just in the positive versus negative direction. Do you know which one it is? Yep, velocity. So let me point out to you that if I look at average velocity over time frame A to B, and I have moved in a positive direction, then this is going to be my position at time B, and this is going to be my position at time A. When I do average velocity, I'm getting a positive change in position over a positive change in time. However, if I was going to the right, this direction instead, then this would be maybe my position at time A and my position at time B. In that case, do you see that the change in position is actually coming out negative? And so that comes down to velocity being positive or negative. So if velocity is positive, we say that the object is moving in the positive direction. The object or particle, whatever you want to call it. And then if velocity is less than 0, then that's when you are moving in whatever is considered the negative direction. Now, this is one of the moments where I'm a little bit embarrassed on what math does. When velocity is equal to 0, we say that the particle is at rest. Even if it is simply for a moment. Now, a moment means no time has taken place. Our physical understanding of at rest includes time taking place. I don't know what to tell you. But somebody decided that we were going to say at rest if velocity was 0, even if it was for a moment in time that doesn't actually exist because moments don't make sense. Anyway, moving on. Speed. What is speed? Speed is the absolute value of velocity. For those of you familiar with physics, you might say that it is the magnitude of the velocity vector. Now, before I hit number 5, I want to warn you that I've been caught in traps where I get to thinking that this is always their question when I see certain phrases. And then one time they threw at me, where is velocity increasing? And I just assumed it said speed and didn't even read the word, because this is what shows up all the time. I just want to throw that out there to be careful. Read all the words. Okay, so if speed is the absolute value of velocity, then if I'm looking at speed increasing versus decreasing, I want to take the positive and negative out of velocity. And this is where I'm going to go to Desmos. And I have a nice little function ready to go to talk about these different aspects. But if time is moving in the positive direction, okay, go away. So if I am moving time in the positive direction and I am looking at the slope and how does the slope change? And if I didn't say it yet, this is the graph of a position function. This is the graph of a position function. That means that the velocity is the slope of the line. The speed is the absolute value of the slope of the line. Now, if I was just asking where is velocity increasing and decreasing, velocity is increasing when I have a positive slope. Velocity is decreasing when I have a negative slope. Velocity is increasing again here with this positive slope. But if I'm talking about speed, I'm looking more about, am I getting steeper or less steep? So right now I'm traveling from some negative time over to this relative maximum, and I want you to watch the slope. Is the slope getting steeper or less steep? And I'm looking in chat. Less steep. What does that mean? Is the speed increasing or decreasing? Right, decreasing. Now, I'm going to start here at this relative maximum, and I'm going to start moving it, and I want you to tell me if, while I move this, I'm getting steeper or less steep. Am I getting steeper or less steep? Steeper. So my speed is increasing over that interval. Now keep watching. Whoa, hey, look at that. Something happened. So at this point right here, we hit a point of inflection, which we're going to talk about more when we get into chapter 4. Ooh, that rhymed. So from this point to that relative minimum, do you see that you are getting less steep? So that means from time 0 to this relative minimum time, my speed is decreasing. And then lastly, whee! And you can see it's steepening, so that would be an example of speed increasing. Now, acceleration. If acceleration is positive, that only says whether your velocity is increasing or decreasing. So I'm going to come over to here, and I'm going to just kind of shout out some numbers of what the slope might be as I move along. Just listen to the numbers. And I'm not going to be, I don't want to sit here and worry about accuracy. But just basically, let's say the slope is -5, -4, -3, negative. Wait, hold on. I can't determine positive versus negative. Wait. Okay, I have a positive slope right now. I can do this. Let's say my slope is like +5, +4, +3, +2, +1, 0, -1/2, -1, -2, -3, -4. Okay, those numbers, are they going up or are they going down? So +5, 4, 3, 2, 1, 0, -1, -2, -3. Right. So from way over here, from -infinity until I reach 0, my acceleration is negative because the numbers that make my velocity are decreasing. Then after I hit this point of inflection, maybe my slope now is -2, -1, -1/2, -1/4, 0, 1, 2, 3, 4, 5, 6, 7, 8. The values of the slope, which represent velocity, are in this case increasing, and that is where acceleration is positive. And what we're going to learn also in chapter 4 is that when your graph takes on the shape of a happy face, do you see how this is a smile? That's when your second derivative is positive. You're smiling when your second derivative is positive. And then over here, when it looks like a sad face, that's when your second derivative is negative. So maybe when people are frowning, we should say, stop being such a negative second derivative. Anyway, going back over to here. So I am going to draw, come on, come back to me. There we are. I'm going to do a real quick draw over to the side of the graph we were looking at. It's not perfect. Something like that. The very important points are relative maximum, relative minimum, and this point of inflection. And I want to point out to you that over this time interval, I have a negative acceleration. After that, I have a positive acceleration. For velocity, when I head up left to right, I have a positive velocity. When I head down left to right, I have a negative velocity. And again, I'm heading up, so a positive velocity. Do you recall which intervals we were steepening? Which ones of these were the intervals where we were steepening? We were steepening when we went from here to here, right? Do you see the slope steepening when you think about it? And the slopes were steepening here to here. Those are where our speed was increasing. Then, what were the intervals where we were getting less steep? Less steep, less steep, less steep, less steep. That's where our speed was decreasing. Now, do you see an interesting pattern that's actually extremely easy to use? I think I need highlights, not hair highlights. What do you notice is the pattern? Yep, that's it. That's it right there. When acceleration and velocity are the same sign, you have an increasing speed. When they are opposite signed, your speed is decreasing. And on an AP exam, when you justify speed increasing versus decreasing, that is precisely what you must use. You must specifically state whether your velocity and acceleration together, what are they, positive and negativeness? You have to say that. So speed is increasing when velocity and acceleration are the same sign. So you would need to state that your velocity is positive and your acceleration is positive. Or you need to say your velocity is negative and your acceleration is negative. And then speed is decreasing if your velocity and acceleration are opposite signed. Which means either you have a positive velocity with a negative acceleration or a negative velocity with a positive acceleration. To continue on, if you are asked for displacement, displacement is flat out just what's your position at time B? What's your position at time A? Subtract. There you go. For you physics people, that is referring to your final position minus your original position. Same exact thing. If you are asked, however, to find total distance traveled, it's a little bit more complicated because if you're going back and forth on a line, the displacement will not tell you at all that that happened. You have to find when you are, quote, at rest. You have to first solve the equation for velocity being equal to 0. And make sure that you're only finding solutions within the time interval. Yes.
It's 10:30.
Shoot. Okay. I'll say this real quick then. Actually, you know what? I'll throw at you the formulas because I hate writing this out anyway. Not kidding. This is what you have to do. If the times that you are having a 0 velocity in order of the smaller time to the larger time between time A and time B, you basically have to look at the change in position from time A to the first time your velocity is 0, absolute value it, plus now from when your velocity was 0 to the next time your velocity is 0, what was your change in position, absolute value it, and add all of those together. Does that make enough sense? And then I will have a video where I go over some of the examples as well. And I need to open up your formative. I need to be careful not to show you the formative. I'm going to stop sharing